First step, we need to draw the external free body diagram because we need to know what the reactions are at A and B in order to draw the total VM diagram for this. We have the reactions A and B vertically. Again, for this unit, we're ignoring everything that's happening horizontally. We'll get into that when we do combined loading in the third unit. And for the external picture, we can simplify that distributed load into just a point load acting in the center. So 150 pounds per foot times 6 feet. We're going to have a total of, down here, 900 pounds. And that's going to act in the center of this. A is going to be 4 feet from the edge. This will be 3 feet, and 4 feet. So from to 11, if we sum moments around A, we're going to be able to find the value for B. It's going to be a positive 200 pound-feet minus 200 pound-feet. So the couples will actually cancel themselves out in this equation. Externally, they cancel themselves out, but internally, they will make a difference here. So they'll cancel each other out, so I won't draw that. I'm going to have a negative 900 times 3 from the distributed load plus 6B. B is 450 pounds. If I sum forces in the y direction, I get A plus B minus 900 is 0. So A is also 450 pounds. Right, so with the reaction solved for, now I can start the construction of the VM diagram. I take my external free body diagram, and I copy it to the top here, putting in the numbers where I need them for the support. So at A and B, I now know their values. At the extreme left, I have the 200 pound-feet. 4 feet in, I have the 450 pounds. I have the distributed load with 150 pounds per foot. It goes for 6 feet. The reaction at B. And then the applied couple at the right edge. The critical lines here are going to be where my point loads are. I want to add those to my graph. The start and the end of the distributed load are also where the point loads are. And the couples are also at the edges, which are already critical lines here. So at least for the V diagram, those are the critical lines I'm going to be using. So I'll start with the V diagram, starting at 0 pounds. Again, I have to look what's happening on these lines and then between the lines, on the lines and then between the lines, to see what the change in the value of V is. So actually, before I do that, I want to look at what the area under this shape is between the lines, which I already found before is going to be a negative 900. And that will make the V step a little bit easier. Okay, so on the extreme left line, I want to see are there any point loads, and that's going to affect the value of V. On this line, there's no point loads. There's a point moment, but that does not impact V. So it will stay at 0 on the line. Between these two lines, there are no distributed loads, so the value of V will not change between the lines. So it stays at 0. On the second line, I have a point load up of 450 pounds. So I'll have an immediate jump in V in that same direction. Between the lines, I'm going to drop by 900. I'm at 450. My change is a negative 900, so by the time I'm on this line, I'll be down to a negative 450. This is a horizontal line. When I integrate it one time, it'll be a first order line or a straight line. So back to being on the line here. So I drop by the 900. I'm on the line. I have a point load up of 450 pounds, which means I'm going to jump up in my value of V by 450 pounds. Between the lines, there's no distributed load here, so it's going to remain at 0. And on this point, there's no point load here, so it also stays at 0. So I start at 0, and I do end at 0. So to aid me in the next step, drawing the M diagram, I want to find the area under my V diagram, since that'll make it the integral that I'm going to use for M. So first thing I need to do is I only want how much of it is above the graph, above 0 or below 0. What I need to do here is going to be pretty simple, but I need to know where the 0 crossing is on V, because that's going to be a maximum or a minimum point on my M diagram. In this case, because I start at 450 and then end at negative 450, what's this length going to be for the triangles?
3.
Right, it's going to be 3 to get to 0, and then 3 to go from 0 to negative 450. It won't always be the case that it's symmetric like this. In that case, we can use similar triangles, and we'll see that in another problem a little bit down the line. But we need to know this 3 because that's how we can calculate what the area is under the positive part of the shape and under the negative part of the shape. So for the positive part of the shape, it'll be 3 times 450 over 2. Right, so a positive 675 and negative 675. Since we're below, so the height of it is negative 450 times 3 over 2, negative 675. We start at 0, and we see, do we have any couples on the line? And we do. We have a 200 pound-foot couple that's going to be in the counterclockwise direction. Remember, this part is a little bit reverse of what you would think. It's positive, or we would say it's a positive couple externally, but internally it's a negative couple. So this will actually cause M to drop by 200 pound-feet. So we go down to negative 200 pound-feet. Between the lines, there's no couples up here, and the integral under the V is 0. So between this line and this line, M will also remain at negative 200. No point couples on the line, so there's no immediate jump in M. But now we've added this extra line here. Between this line and this line, the value of M will increase by 675. So we are at negative 200. We go up by 675. So that will take us to 475. We said these are first order lines or straight lines in the V diagram. When we integrate it, it goes up by 1 order. So they're going to be quadratics or second order lines. And then this gets to your question from before. Again, how do we determine what the slope is or what the concavity of it is? We have to think in the opposite direction. The value of V is equal to the slope of M. So at this point, the value of V is 450, which means that the slope of M is 450. Again, this is just a sketch. It's going to be a rough estimate as to the slope. So it has some positive slope here. The value of V here is 0, which means the slope of M here is 0. So this tells us the concavity of our shape because it goes from a positive slope to a 0 slope, which means that that's going to be the general shape of the curve. If it went from a 0 slope to a positive slope, then it would have this concavity to it. So that's how we determine is it concave up or concave down. So we go up to 475. On the line, there's no point couple here, so there's no jump once we're at this maximum. But between the lines, now we're going to drop by 675. So we actually will go back down to negative 200. Same idea as before. We start with a slope of 0, and we're going to end with a slope of negative 450. So down here we have a negative slope. So again, that is going to determine what the concavity of our curve looks like. No point couple on the line, so no jump. Between these two lines, there's nothing happening in V, so we were going to remain at negative 200. Finally, on this line, externally, negative 200 pound-feet, which means it's the opposite internally. So it's clockwise, which means we jump up by 200 back to 0.